The key to any optimization is to come up with a merit function or a cost function that makes some sense and is solvable. So we came up with a cost function for ordinary least squares that doesn't actually make sense, but it is solvable. And then we came up with a cost function for the weighted total least squares that makes a lot of sense, but isn't solvable. And then in the last section, we basically got rid of the arbitrary weighting, and we looked at total least squares with a fixed weighting, and we just called that TLS. And that was a cost function that made sense in that scenario, and it was solvable. So we had both properties there. That was fantastic. And would like to come up with a cost function that makes at least some sense and is solvable in the more general case when there is different weighting between sigma xi and sigma yi. They don't have to be the same thing or proportionally related all the time. We want something that's recursive and feasible for implementation and so forth. In this section, we're going to quickly set up a cost function that makes sense, I hope. It's not doesn't make quite as much sense as the weighted total least squares cost function we started with, but it makes a fair amount of sense. And it is solvable. In the next section, we will spend more time with this cost function and solve it. So here our concern is only the cost function itself. This section is all about geometry. All about geometry. If we go back and look at the original weighted total least squares solution that makes sense but is not solvable, we have this picture here in our minds. We have data points that are drawn. They've got error bounds in the x and y direction that are drawn. And each one of these data points must map somehow to the capital Y equals Q capital X line. But we said that the mapping was optimized as part of the process. The mapping was not deterministic as it is for ordinary least squares. And the mapping might be as shown. You can see the dotted lines, for example, connecting the data point to, so the data point there to its map on the line. And these mappings don't all have to be parallel to each other or have any special properties at all. It's just optimized. And we saw how it was optimized by using Lagrange multipliers and taking derivatives of parts of the equation and so forth and solving. So we did that and gave us a great answer, but it's not easily computable in any kind of recursive way. Then we said, well, let's drop the W. Let's look at the total least squared solution when the sigma x squared and the sigma y squared are always proportional to each other. It is still weighted, I guess, but it's not weighted in the same arbitrary way. It turns out, if you look at the solution to that problem, we have the geometry that's shown in B. And I think specifically that's when we assume that sigma xi and sigma yi are equal. By the way, I'm probably going to leave the screen focused on this image here for a while, even though I'm going through the text on the sides, so you might kind of look ahead as well and see, oh yeah, he's talking about that now. Notice what happens in B. If so sigma xi equals sigma yi always. Now they could be different for every data point, but they're, sigma x1 is equal to sigma y1, but sigma x1 is not necessarily equal to sigma x2, and so forth. But the proportionality is the same in every case. Very, very interesting. When you look at the map, we have that the best thing to do, now I'm plugging this assumption into this solution. I'm not making this up from scratch. I'm just saying use the old solution but put in this assumption, and we get that all of the data points are the line that they map to, or the point that they map to on the line, turns out that there's this perpendicular relationship between that line and the slope y equals qx. We have this perpendicular geometry, and that's what causes everything to fall apart, and you get some nice, beautiful result because of that. Okay. Perpendicular might be key. What we're going to do when we look at approximating the solution, this here applies to the general case, this applies to the specific case, but I would like to take this idea and apply it back to the general case approximately in order to get a computable answer in the general case. Again, I'm going to have a data point xi, yi, where, whatever that is, and that is going to map to some point on the y equals q hat x line, but we are going to constrain the mapping onto the line such that we preserve a right angle there. So we're adjusting the slope q to preserve a right angle. Now, of course, I could adjust the slope. The slope could be like this, and then the mapping would be like that. It would still be a right angle, but it would map to a different place. And so we're going to optimize something. So again, we are weighting the uncertainties in each direction, but we are enforcing this right angle connection to the line, and that is going to make the math fall apart in such a way that this is solvable. I'm looking ahead to the next page, and I'm somewhere in the middle of the next page of text now. So we've started talking about frame C. Frame C here is illustrating the definitions that we are going to use inside of our approximate solution. This is the idea, and these are the definitions. We weight the distance between xi and its map on the line differently from the distance between yi and its map on the line. Here we weighted them the same, but here we weighted them differently, and here we're going to weight them differently as well, but still enforce this right angle geometry. This is going to give us a better total capacity estimate than the middle solution, the frame B solution. So we make some definitions, and there's a lot of different triangles here, so it's tricky to keep them apart. But again, our data point, xi, yi, is there, and the horizontal distance between that point and the line is delta xi. The vertical distance is delta yi, like that. The slope of this line here, you can see, it's rise over run. So it's delta yi divided by delta xi. That's what q hat is. So this is equal to delta yi over delta xi all times x for every data point. That's going to be true. And we can find that the angle of the line is the inverse tangent of q. So we know that the angle here, this theta, is the inverse tangent of the rise divided by the run, so delta y divided by delta x, but we said delta y over delta x is q. So theta here is equal to inverse tangent of q. The shortest distance between the line and the data point is along here. That's the shortest distance. We call that r sub I. And we'd like to have an equation for r sub I in terms of some of these other things. And if you notice doing your triangle math, if you look at this triangle here, I've got theta This is 90, so this has to be 90 minus theta. And if I look at this triangle here, well, that's 90, that's theta, so this must be 90 minus theta over there. And if I look at this triangle here, I've got 90 and I've got 90 minus theta, so that angle must be theta. So let's keep it on that triangle for a minute. I'm trying to find this base length here. So that's going to be the hypotenuse times the cosine of theta, and the hypotenuse is delta y. So we have Ri equals delta yi cosine of theta. Okay, so far so good. But theta, we said, was equal to the inverse tangent of q. So I have that tan theta equals, theta and q look the same when I write them that way, don't they? Tangent of theta equals q. And so this here is equal to delta yi cosine of tangent of this is cosine theta. It's the cosine of the inverse tangent of q. And the cosine of an inverse tangent of something, you can work out the triangle math again, and it turns out that this is equal to delta yi over square root 1 squared plus tangent squared theta. And tangent squared theta is q squared, so this is delta yi over square root 1 plus q hat squared. Wow, all of that, but we have an Ri in terms of things that I would like to find, q, and things that can be found from the data. So I've defined this. It remains, and I've defined that, and I've defined that. It remains to define these little delta xi's and little delta yi's. So let me erase a few of these lines here to clear things up a little bit. We'd like to find this distance, which is the distance, the horizontal distance between the data point and its map, between little xi and big Xi. And we'd like to find this distance, which is the difference between little yi and capital Yi, and that's called little delta yi. Those two distances. And if we look at this triangle, I've got Ri as the hypotenuse, and this angle here we said was theta, and this here is the height of it. So we're looking at this triangle here now. Then the delta xi is going to be Ri times the sine of theta. And if we look at this triangle here, we would have, because this here is theta, no it isn't, yes it is, has to be theta, so that we have that the delta yi is equal to Ri times cosine of theta. So you might want to spend a little bit of time just reviewing all of that, some scratch paper on the side, but I believe that all of those definitions are accurate. With those definitions, I'm going to skip ahead now to the third page. We've talked about all the points on those 2 pages. We are going to define a new merit function. Here is our new merit function. We are summing all the data, I equals 1 to n, of the x distance between the data point and its map on the line, and the y distance between the point and its map on the line, each one normalized by their own sigma x squared and sigma y squared, where we no longer assume that sigma x squared is proportional to sigma y squared. We treat them independently once again. We are causing it to be a right angle map, but we are saying that the weighting doesn't have to be proportional. Well, we're almost there. This delta xi squared, if we go back and we say, well, what was delta xi again? It was on the previous page. Delta xi equals ri sine of theta. So delta xi squared, oh, and we had that, we know what ri is. So ri equals delta yi over square root 1 plus q squared. So that means that delta xi is equal to delta yi sine of theta over square root 1 plus q squared. And we know what cosine theta is. We said that cosine theta is equal to 1 over root 1 plus tan squared theta. So when I do the sine squared, it's 1 minus cos squared. So when I square all of this, I'll get a delta yi squared from that. I'll have this squared from that. And then the sine squared is 1 minus this squared, which is going to give me that when I multiply through. And the delta yi squared, you go through the same steps, and you get the little delta yi squared gives you the big delta yi squared over 1 plus q squared, all times 1 over 1 plus q hat squared. Okay, we have all of those. And we know that big delta yi is the vertical distance between the data point and the line. We said that, so that's little yi minus q hat xi, that's what that is. And we plug that in there and in there, and we divide by the sigma x squared and the sigma y squareds, and we factor stuff around and so forth. And in a couple lines of algebra, not too many lines, we get this cost function right there. The approximate weighted total least squares cost function is this one that's given here. We acknowledge that this is not identical to any of the cost functions we've seen, except because of the property of the weighted total least squared solution, when the sigma xi and sigma yi are the same, we would expect this to be the same for that case at least. So we can do that. We can put in a sigma yi in here, sigma squared yi. Oh, I've got the same denominator, so those combine. Oh, the numerator is q squared plus 1. That cancels out one of these in the denominator. So this goes away, and I'm left with a sigma yi squared there. That's all that's left. When you compare this to the cost function we had before and said, oh, it's exactly the same. So at least in one case, this cost function is the same as what we've seen, but not in every case. So we have to say that this is approximate, it's not exact, and it remains to be seen when we do the solution and the simulations how well it's going to perform. The solution turns out not to be the same when there's a constant proportionality between sigma xi and sigma yi. But that is something that we can correct in the final answer to make it the same for this case and this case by a very simple manipulation. So that preserves some of the properties we would like. So if you follow that, the geometry involves a bunch of triangles, but if you followed all the triangle stuff, we have a new cost function, and that was the biggest part of the battle. The rest of this is a bunch of straightforward algebraic manipulations. In fact, we're going to ask Mathematica to help us quite a bit. The really important thing is coming up with a cost function that makes some sense And of course, it remains to be seen if this leads to a simple solution. In fact, it does lead to a simple solution, so that makes everything that we've done here worthwhile. So let's proceed. Let's go and look at the solution, and then after that we'll look at a number of examples.